All right, so this is the sample exam that was posted in the chapter 4 module. There's actually a second practice exam too, so you're welcome to work through both, and the key is posted. But what I thought might be good is just for us to work through this as a group, and then if any questions come up, you can stop me, interject, and then we can also spend some time at the end to go over any additional questions that you have. Keep in mind that because this is an online term, my exam will be more like your homework and quizzes. You won't be asked to show work necessarily. So just kind of anticipate the exam to be a lot like a quiz plus. So it'll be what you're used to up to this point. So let's go through the first question here. So what are the two characteristics of matter? There's one that's easy to remember. All matter must have mass. What's the other one? Does anybody know?
Volume.
Volume, exactly. And really, those are the two things that we must have if we're talking about matter. We must be able to get a mass, and we must be able to get a volume of it. All right, and next one. Which of the following is a physical property? So a physical property, if you remember, doesn't involve changing a substance into a new type of substance. So let's take a look at A. So ethanol or ethyl alcohol is very flammable. Did that involve a change? Yeah, I'd say we'd be burning it, right? So I'd say that's not a physical property. It involves a change. All right, metal used for artificial hips is not corroded by bodily fluids. Corrosion is actually a chemical process. So I'd say that's a chemical property. And then the next one says a 1.00 centimeter cubed of aluminum weighs less than 1 centimeter cubed of lead. Did that involve a chemical change of any sort? No, I'd say that's just a casual observation. So I'd say, yeah, I'd pick C, but let's check the last one. Neutralization is a chemical process. So that'd be a chemical property. Cross that one out. And then E is just none of the above. So I'd go ahead and pick C for this one. Make sense? All right. The smallest unit of a compound that has the chemical properties of that compound is what? So basically, what's the smallest thing we can chop it into without losing the nature of the substance? So let's imagine H2O, right? So H2O would be a good example of a compound we're all familiar with, right? What's the smallest thing we can chop it into and still have it behave like water, H2O? Would it be a proton, atom, electron, molecule, or neutron?
Atom.
Not quite. In fact, if we split this into hydrogen, hydrogen's a gas, right? And hydrogen's an explosive gas. So that's the one that tricks a lot of students up. We can't actually snip those bonds and have water behave like water anymore, right? So in this case, I would say the best answer would be molecule. But that is something that a lot of students get hung up on. They want to pick this one because that's the smallest thing that we can split and have an element behave like an element. But this one's specifically asking about the properties of a compound. So a molecule is going to be the smallest unit there. All right. And feel free to jump in if there's something that doesn't make sense too. So 4, calculate the density of an irregular object weighing 84.153 grams, and the object was immersed in a graduated cylinder of kerosene with an initial volume of 19.7 milliliters and a final volume of 31.9 milliliters. Okay, so let's kind of walk our way through this because there's actually a curveball in here. They're trying to distract you. Let's first define density. So density, we know, is going to be mass over volume, right? That's our standard definition of density. Good thing is they give you the mass here, right? They tell you that it's 84.153 grams. So I'll just go ahead and plug that in. And now we need to find the volume of the irregular object. So this is kind of interesting. Do you think we need to use the density to find the volume here? Or is that just completely unnecessary? Does anybody want to chime in?
I thought it wasn't necessary, but I think I might have done it wrong.
No, I think you're right. We don't need this, right? Because they give you volume here and volume here, right? So just like we did in the pennies lab, in order to find the change in volume, we're just going to subtract the two, right? But I'd say them giving you density was just to distract you. So let's go ahead and subtract these two. So the final volume was 31.9 milliliters. We're going to subtract out 19.7 milliliters. And let's go ahead and do this in our calculator. I'm just going to keep the top as is, but let's subtract on the bottom. So it's 31.9 minus 19.7. I'm getting 12.2. And we've got it set up to do our final calculation, right? But we're not quite done. Let's do this in our calculator. And I'm getting a giant number out of this. I'm getting 6.897786885 grams over milliliters. How many sig figs should we have, though, in our answer?
3.
Yeah, 3, because when we look down here, this number only has 3 sig figs. It's going to limit the number of sig figs in our final answer because we're following the multiplication and division rules. So let's go ahead and change this. I'd say 6.90 grams per milliliter. This has 3 sig figs. We're going to count these 3, but then because this is greater than 5, we need to round up, right? So a lot of students forget that last rounding up step. Sound good? Okay, let's do the same thing for the next one. The next one is going to assume that all of these are measured values, not just absolute math values. So how many sig figs would we predict for this calculation here? How many sig figs should be in our answer?
3.
3. I would say 3 because here we've got 3 sig figs. Oops, sorry, that's kind of messy. Here we've got 4 sig figs, and here we've got 5 sig figs. So the final answer should only have 3 sig figs. But let's do this in our calculator. So 0.1432 times 2.83 divided by 7.7621. If I go ahead and get my full answer without sig figs factored in, it's going to be this. But if we trim it down to 3 sig figs, we would only include these last digits. So the final answer would be 0.0522. Make sense so far? If anybody has questions on sig figs, feel free to ask me too.
In this case, we can use, well, it says to do scientific notation.
Oh, shoot. Yeah, you caught me. I wasn't even reading this answer fully. So thank you. Scientific notation, we're not done yet. Okay. So we need to move this decimal over past the first non-zero digit, right? So in this case, we're moving it 2 places to the right. So this would be 5.22 times 10. And then because we're moving it to the right, that exponent is going to be negative. So it'd be 10 to the negative 2. So this is the correct answer in scientific notation. Thanks for whoever caught that. I wasn't sure who said that, but thanks for chiming in. Awesome. So we're making
about the sig figs.
What's that?
I got a question about the sig figs. I got stuck in my head that basically any zeros that are on the far left of a figure, whether there's a decimal or not, aren't significant. Anything that is found on the right is significant. But is it that simple? Am I missing something there?
No, that's a good point. There's a little bit of nuance to it. So let's think about a couple different numbers. So 0.0051, right? these right here are not significant.
Okay.
All right, let's do another number now. Let's do 5,000, right? In this case, these are not significant
Okay.
because there is no decimal.
That's the hinge then, huh?
Yep. If we had 5,000.0, then all of a sudden, these are significant.
Including the one to the right of the decimal.
Exactly.
Okay.
Oop, because there is a decimal. Exactly. So that's the thing that throws people off is leading zeros, meaning to the left, are never counted under any circumstances. But when we're looking at zeros to the far right, it depends on whether or not there's a decimal. If there's a decimal, they're counted. If there's no decimal, then zeros on the far right aren't counted.
And that's about it.
Yep, that's it.
Jesus.
Yeah.
Overthinking it. Okay, thank you.
Yeah, no
Muting.
problem. All right, so let's keep going. We're on number 6. How many millimeters are in the basic metric unit of length, the meter? So we can write this out a few different ways. If we think about the term milli, the prefix milli always stands for 10 to the negative 3. So we could say 1 millimeter is 10 to the negative 3 meters, or 1/1000th of a meter. Conversely, we can change this, right? We could say that we could write this and say that there's 10 to the 3rd millimeters in 1 meter. These are mathematically equivalent, right? So we could just write this as our final answer there. I'd say this would be good enough. So make sure with that chart that you do try to memorize those general prefixes. I don't want you to memorize everything on the chart, just the ones that I highlighted on that video. All right, number 7 is a tricky one. This is one that students often struggle with. It says, what's the percent nitrogen in caffeine? All right, so what we should do first, I would say, is let's figure out the total mass of this molecule. So in order to do this, we need to really focus in on the molecule itself. Whoops. And what I'm going to do is break it into parts. So for carbon, we've got 8 atoms. And if you go to the periodic table, 1 carbon atom is 12.01. And then next we'll look at hydrogen. And we've got 10 of them, and they're 1.01. Depends on your periodic table. Sometimes you see 1.008. I'm fine either way. You should be able to get to the right answer here. And then nitrogen, we've got 4 of them, and they're 14.01. And then we've got oxygen. We've got 2 of those, and they're 16.00. So let's go ahead and add up all of these. So let's do 8 times 12.01. That's 96.08. And then 10 times 1.01, it's just 10.10. And then 4 times 14.01 be 56.04. And then the last one, 2 times 16 would be 32.00. All right, now what I want to do is let's add this all together. So let's focus in on these and add them all together. All right, so I've got 96.08 plus 10.01, or sorry, 10.10 plus 56.04 plus 32. It looks like the total molecular mass for this would be 194.22 AMU, or grams per mole, however you want to write it. All right, but now it's asking what's the percent nitrogen for this. So let's think about percent a little bit. So percent oops, sorry, my pen's not doing its thing, is always going to be a part divided by a whole times 100, right? So let's think about the percent for this situation. What is the part going to be that we're trying to find? Well, it sounds like we're trying to find nitrogen. So when I go over, it looks like nitrogen for this compound is making up 56.04. That's what it's contributing to the overall mass, right? So I would go ahead and plug that in on the top. And then the whole is just going to be the mass of the whole entire molecule, which is going to be 194.22 times 100. So let's go ahead and do this in our calculator. So 56.04. I'm getting a percentage of 28.85. And I'm also keeping in mind Sig Figs. So I'm limited by 4 Sig Figs here. So I'd say this should be my answer, but let's see if that's one of the multiple choice problems. Yep, looks like 28.85 is right there. So these ones, don't let them freak you out. Oftentimes you just have to go slow. I was telling somebody earlier today during office hour that one mistake students make when they're doing multiple choice is they don't use scratch paper. I always tell students, treat this like a normal in-person exam. Have a periodic table out, have a scratch paper out, and try to work through the problems by hand, even though you're not going to be submitting your written work. It's just good practice to get into. All right, number 8 is hopefully a little easier, less mathy. A blueberry bagel may best be described as what? It's definitely not an element. I don't see blueberry bagels on the periodic table of elements. It's not going to be a compound. We can't write a molecular formula for a periodic or a blueberry bagel. And then the question is it going to be homogeneous or heterogeneous? And remember, homogeneous means the same throughout.
Heterogeneous.
Heterogeneous, exactly. The fact that there's like little individual blueberry chunks means it's not the same throughout. So this would be a heterogeneous mixture. All right, number 9, you've collected 195.3 milliliters of mercury, and it looks like this person's trying to sell it for 41 cents per 100 grams. How much would you get? All right, so this is a typical conversion problem, and a lot of times students are really uncomfortable with these because there's a lot of numbers and it's hard to know where to begin. But I always tell students with these problems, always start with what you have and what you know, okay? So what I immediately know I have is this amount of mercury. So I'm just going to go ahead and plug that in and we'll figure out where to go from here. So 195.3 milliliters of mercury, and the elemental symbol for mercury is Hg, so I'm just going to abbreviate it like that. So that's what I'm starting with. And I know I'm trying to figure out how much would you get, meaning how much money would we get. So I'm going to have to cancel out milliliters of mercury. That's going to be my first step, is to get rid of that unit, right? So then the question is, what conversion factor do I have where I could convert milliliters into something else? Well, there's 2 different conversion factors that they're essentially giving you in this problem. The first one is right here. That's the density. It's the relationship between mass and volume, right? So you could use that to do a conversion. And then the second conversion they give you is dollar per gram. So in this one, we can't use the dollar per gram because that really doesn't fit in with the units that we have. But we could use density. Specifically, it said that there's 13.534 grams in every 1 milliliter of mercury. That's what the density was given to us as. So the fact that 1 is paired with the milliliter unit means that 1 must be paired with the milliliter unit here. And then we can plug in 13.534 grams on top. Okay, so now we've canceled out milliliters and we're on the right track. But now I want to get rid of grams. So I'm going to put that on the bottom. That way we can cancel here and here. And I want to figure out how much money I can get for it. So that's my desired unit on top. So we've already used this conversion factor, but now we get to use our second one, the dollar per gram. So we said that there's $0.47 for every 100 grams. So I'm going to put the 0.47 with the dollar unit because that's what it is with the conversion factor. And I'll just put that on top. And then I'd put 100 on the bottom with the grams unit. It's really, really important that you keep the units paired with the correct number. So for example, 100 was paired with grams and 0.47 was paired with the dollar unit. A lot of times students will flip-flop them because they forget to double check that. So now when we're done with our setup, we can see our remaining unit must be dollars. And let's go ahead and plug all of this in. So 195.3 times 13.534 times 0.47 over 100. Okay. And if we round it to the nearest penny, this would be $12.42. So that's how much money that person would be able to get if that person tried to sell this mercury to whoever was buying it.
So my question,
Yep.
my question here, is there a reason we wouldn't use the significant figures of the 47 cents and just make it $12?
Yeah, that's a good question. If you did put $12 for this one, I would give you credit personally. Oftentimes, Sig Figs with money, they just go out to the cent because it's kind of a predefined number of Sig Figs that's common with money. But I would accept either answer. Go ahead.
Okay, if we were, because that just for showing our work, I just did it the other way. I did like the millimeters, the 195 millimeters, and then I times it by the density. And then I divided it by 100 and then times it by 0.47.
Yeah, I think that would be fine. Ultimately, as long as you get the right answer, that's really what I'm aiming for. Yeah. I know some students like to set it up a little differently from how I have it shown, and that's fine with me. I would say if you're consistently getting the wrong answer when doing conversions, you might want to try to simplify it and maybe follow the way I'm doing it. But if you've got another way that's working reliably, go for it. I know my wife and I were even joking because if any of you have kids in elementary school, they like changed all of math recently. Oh, really? And so sometimes we get students coming in from running start showing us like multiplication. We're like, what are you doing? I've never seen this before. But we just learned to deal with it. As long as it works, it works. All right. Next one's number 10. What are the three fundamental particles making up an atom? So let's think about an atom. What are the different components that make up an atom? Does anybody remember?
Protons, neutrons, and electrons.
Yep. Protons, neutrons, and electrons. All right, and we said that protons have a positive charge, electrons have a negative charge, and then neutrons have no charge. And then these are in the nucleus, meaning the center of the atom, while electrons are around the nucleus. So those are the most important features I want you to remember of an atom. If you go on and take super advanced physics, you may talk about subatomic particles even beyond this, but for this course, these are the three most essential particles I want you to know. All right, next one, calcium chloride. What is the correct formula? So let's break this apart. So calcium, If we look at the periodic table, it's in group 2A, meaning the second column over. So what charge will calcium always have? Must be 2, right? So I'd say because it's in group 2A, it would be 2 plus. Another way of thinking about this is, let's imagine calcium by itself. It's got 2 electrons, right? It's not happy having 2 electrons. It would rather have an octet. So it has a choice. It could gain 6 electrons to get an octet, or it could just dump off the 2 that it has to get an octet. Is it easier to gain 6 or lose 2? I'd say it's a lot easier to lose 2, which is why it has that 2 positive charge. Okay, and then next, we've got chloride, which is in group 7A. So it has 7 valence electrons, same idea. It could either lose all 7 of its electrons to get an octet, or it could gain 1. I'd say gaining 1 is going to be a lot easier, which means it must be Cl1 minus as an anion. Okay, so now we've got to figure out the formula. And the most important thing to remember with these is the charges must cancel out. So are they happy right now in a 1-to-1 ratio? I'd say no. The calcium has 2 plus, the chlorine only has 1 minus. But what we could do is, what if we just double up on the chlorines and have 2 of them? Now we've got 2 1 negative charges that could bounce out the 2 positive charge. So if we take this all together, I would say that this is going to be CaCl2, which it looks like that would be A. A lot of times students would on accident say that it should be CaCl. Not quite. We need 2 chlorines in order for this to be a neutral, happy molecule. All right.
I have a question.
Yeah, definitely.
About the octets. So in one of your videos at one point you said boron or something was cool with not having 8. How are we supposed to know which ones are okay with not having an octet?
That's a good question. My general rule of thumb is I'm never going to try to trick you.
Okay.
I'll try to give you some sort of guidance with that, or it'll be very intuitive.
Okay.
Yeah. It does bug me that so many books call it the Octet Rule. It's kind of like octet normally, but there's a lot of exceptions.
Okay. Thank you.
Yeah, no problem. The other big exception is hydrogen. Hydrogen never has an octet. It only has 2. And that throws students off sometimes too. So next one, how many neutrons are found in the nucleus of a phosphorus 29 atom? And this 29, if you look at it, is the mass number. And the mass number is going to be equal to the protons plus the neutrons. All right. If we look at phosphorus, phosphorus might have a varying number of neutrons. That's what accounts for isotopes, right? But it always has what number of protons? Well, we could look at the periodic table and we could say, well, the atomic number is always going to be the same as the number of protons. So on the periodic table, it looks like phosphorus is number 15. So what I would do is I'd say, well, we know the mass number is 29. We know the protons is 15, and I'll just call the neutrons X. So really, to find this, we just need to do 29 minus 15, which would be what? 14? So we could say that there must be 14 neutrons in this phosphorus 29 atom. And then number 13, atoms are neutral. How can ions exhibit charge? So a charge basically means that things are no longer balanced, right? Meaning things are either overly negative or overly positive. What could cause this? A says atoms are not really neutral. I don't know if that's the greatest answer. Different number of protons and neutrons? Not necessarily. C says different number of neutrons and electrons? Not necessarily. But D looks like a good shot, because if we don't have an equivalent number of electrons and protons, they won't cancel each other's charges out, and we'd end up with an imbalance of one or the other, right? So that's how ions exhibit charge. Make sense? I'm going to assume the silence is yes, unless somebody chimes in. I miss teaching in person. Isotopes differ from each other in what way? They have a different number of protons in the nucleus, different number of neutrons in the nucleus, or different number of electrons. Let's assess all three of these. So if they had a different number of protons, would they be isotopes? No, they'd just be different elements altogether. Different number of neutrons? Yeah, definitely. They could be the same atom, but a different isotope. Different number of electrons? No, that would still be the same element. It would just have a charge, potentially. Then 15 is another conversion one. So this one will take a little bit more work. But let's try to start out with what we know. I know that I've got 3.011 times 10 to the 23rd atoms of fluorine. And it's asking what would the mass be? So I want to get rid of atoms. And I want to get to my mass. So there's a couple different ways you can do this. But anytime we're converting from number of things, we need to use what number? Does anybody remember that number?
Avogadro's number.
Yeah, Avogadro's number is really helpful when we're moving from numbers of things. And that's 6.022 times 10 to the 23rd atoms is equal to 1 mole. Okay, so we could go ahead and plug this in and we could say, well, 6.022 times 10 to the 23rd atoms of fluorine would be equivalent to 1 mole of fluorine. By doing this, we can cancel out our atoms, and now we've got to moles of fluorine, and we've used Avogadro's number to accomplish this. But it's not asking what would the mass be, it's asking what, or sorry, it's not asking what the moles would be, it's asking what the mass would be. So let's go ahead and cancel out moles of fluorine and figure out grams of fluorine. And how would we find this? I'd say let's just go to the periodic table and look up the atomic mass of fluorine. All right, so on the periodic table, it says it's 19.00. And what that means is that there's 19.00 grams of fluorine and 1 mole of fluorine. So now I'm set because I can plug in the 19.00 here, get 1 mole on bottom, cancel out our moles, and now we're left with our grams. So let's go ahead and plug this all in. And I'm getting a number that's 9.5 grams of fluorine. That's not quite right yet. And in fact, I know it's not right because it's not any of the potential answers. What's wrong? Anybody spot a mistake?
Significant figures?
Yeah, significant figures. So it could have more significant figures. So in this case, it is a little bit weird. I'd say this has 4 sig figs. This has 4 sig figs. This has 4 sig figs. So really, what I would do is write it out like this. It doesn't look like there's an exact answer for this. I wasn't the one who wrote this test. I actually borrowed it from another professor, but we'll assume that they probably meant B on here, right? That seems to be the closest match here.
If you were going to ask this, now I know you say you're not looking to like trick anybody or anything, but if you were going to ask this, would you be looking for the answer if none of the above is correct?
No, I would probably say that if you see one where the difference is so negligible like that, and it's just a sig fig thing, go with the answer that's, it looks correct, but just is missing a sig fig.
Okay. I was nodding the whole time, but I just realized I had the camera off. So.
Oh, no, that's
okay,
fine.
Thanks.
All right, 16. What is the location of silicon on the periodic table? The period number and the group number. All right, so let's start with group number. That one's easier. And group number basically says, where is it in the columns? So let's actually go to our periodic table. Sorry, it's up here somewhere. Here we go. So silicon, I would say, is in group 4A, right? Because if we look at it, silicon's right here on the periodic table, so it must be in group 4A. And then the period number. Number one mistake I see students make is they start counting down and they say period 1, period 2. Not quite, right? Because they forgot about that row of hydrogen. So what you would want to do is go all the way over here and say, it must be in period 3, but group 4A. So let's go ahead and just write that in our answers. Here we go. And then the period number we said is going to be period 3, not period 2. So
And
watch out. What was that?
you would prefer to see groups written as Roman numerals, not the number 4.
Personally, that's my preference. I will say that on an exam, you can actually print out the periodic table. And because it's multiple choice, it'll probably make sense if you're not seeing Roman numerals to use the other number.
Okay.
Normally what I do for exams is questions are pulled from a question bank. So you might not get the same problem as somebody else. So sometimes there's quite a number of questions in there. So I'd have to go back and double check, but I think they're Roman numerals.
Okay.
Yep. The maximum number of electrons that can occupy a representative element's valence shell. Let's first define what a representative element is. Does anybody remember what that is? It's kind of tricky.
To the far left and the far right.
Yep. So far left. And what I mean by far left is that's called the S block. It's the first 2 columns. Oops. And then the far right is going to be the P block. But it doesn't include any of those transition metals in the middle, and it doesn't include any of the lanthanide and actinides underneath the periodic table. Those aren't included. Okay, so let's keep that in mind. What's the maximum number of electrons that one of these atoms can have? Is it going to be 2, 4, 6, 8, 10, or the correct answer is 8? Does anybody have an idea for this one? I would say 8. So the octet rule says that representative elements typically only have 8. The one that varies above 8 are the transition metals. Those can go above 8 because they've got the D block that can actually fit more electrons. But for our class, we're not really going to worry about that beyond just electron configurations. Make sense? But if you think about the S block has 2 electrons. And the P block can have a maximum of 6 electrons. So if we add these 2 together, the most you could ever have is going to be 8 electrons from those in the valence shell. So that's another way of thinking about it. All right, formula weight for potassium chloride in AMU. Well, let's first define the formula for this. So potassium is one of the weird elements that starts with a K from the Latin word. I can't even remember what it is right now. And then chloride is going to be Cl. But let's double check that we've got the charges and the numbers correct. Potassium is always in group 1A. So it's going to be 1 plus. Chloride's in group 7A. So it's always going to be 1 minus. So it looks to me like the charges are already balanced, which means that the formula for this is just going to be KCl. Okay, so now what we can do is we can say, all right, potassium, we've got 1 atom, and we'll pull up the periodic table. It looks like it's 39.10. And then chlorine, we've got 1 atom. Pull up my periodic table, and it's 35.45. So really, this is pretty easy. I'm not even going to bother with the multiplication. I'm just going to add. So 39.10 plus 35.45. I'm getting 74.55 AMU. The book oftentimes just calls it U rather than AMU, but really it's the same as the numbers you see on the periodic table with the decimals. All right, number 19, again gets back to the representative element question, where we said that a representative element is going to be anything that resides in the S or the P block, meaning the far left or far right-hand side of the periodic table. All right, so let's first check. Element 30, I'm going to pull that up on my periodic table. Element 30 is zinc. It looks like it's in that middle portion of the table. So we said the middle portion doesn't count, right? So I'll cross that out. Then element 26 is iron. Again, that's in the middle portion, so that doesn't count. Element 38 is strontium. Would that count? Yeah, I'd say that's in group 2A. That's in the S block, right? The first 2 columns are in the S block, so I'd say that counts. But let's check element 63 really quick. So element 63 is actually underneath the periodic table. Underneath the periodic table doesn't count. That's the F block. So we'll cross that out. All right, number 20, calculate the molar mass of 1 molecule sulfameter. All right, so this one's going to be similar to what we did in the previous problem, but they've already given us the formula. So let's go ahead and just list all of the element types in here. We've got carbon. We've got 11 of those. Hydrogen. It looks like I've got 12 of those. Then nitrogen. Got 4. Oxygen. I've got 3. And then sulfur. I've got 1. So that's the number of elements for each, but we need to multiply them each by their atomic weights on the periodic table. So carbon is 12.01. Hydrogen is 1.01. Nitrogen is 14.01. Oxygen 16.00. And sulfur, I can never remember sulfur. It's 32.06. So let's go ahead and add all of these, or multiply all of these. So I'll do the carbon first. So that's 132.11. And then 12.12. And then 56.04. And then 48.00. And then 32.06. So now I can just go ahead and add all of these up. And I'm getting 280.33 AMU. Is that checking out with everybody?
Would you cancel one of the 3s for the Sig Figs, or would you?
Yeah, that's a good question. Because we're doing addition right here, what I would say is this number goes 2 to the right, 2 to the right, 2 to the right, 2 to the right, 2 to the right. So I would stick with 2 to the right in my final answer. Yep, good questions. And it is tricky. It really depends on the periodic table that you're using too. So some periodic tables have these numbers right here that go out to many, many more decimals. So I just say try to follow the rules as best you can with your periodic table, but I'm not going to be super nitpicky if you're using a periodic table that's different than mine. Okay. So this instructor did extra credit. I'm trying to remember if I had extra credit. Normally I don't do much extra credit. I'd rather drop assignments like a bad quiz or bad exam. So that's why I typically don't do extra credit. I find that it really just helps the top students, doesn't help the students that are struggling. All right, so 21. A molecule of ethyl ether represented as C4H10O may be classified as what? So what does it mean when it's heteroatomic? That's the first term I'm seeing here.
In essence, it's a compound.
Yeah, it means it's made up of different types of atoms, right? Or it's a compound. And then monatomic means only one compound. So really this doesn't make any sense. So I cross out A. Next one says homoatomic and polyatomic. So homoatomic, I would say this isn't homoatomic. It's made up of carbon, hydrogen, and oxygen. So I'd immediately throw this out. Same thing with this one. But then we get down to D, heteroatomic and polyatomic. So heteroatomic means made up of different types of atoms. Polyatomic means many atoms. So I'd say that D would be the best answer here. Sorry, going back to monoatomic just means one atom. So in this case, it's definitely more than one atom. All right, definite volume, indefinite shape is a characteristic of what type of matter? So do solids have indefinite shape? Do they move around? No, I'd say not a solid. We haven't really talked about plasma at all. Does anybody know what plasma is? It's a superheated gas. So if you are into astronomy and you look at like a nebula with all the glowing gas around a star, that's a plasma. A more common plasma that you might be familiar with is fire. We haven't really talked about it though, so we're just going to leave that off too. All right. So gas, I would say, doesn't have a defined shape. Gas is going to occupy whatever you put it in, so that might work. But does gas have a definite volume? I don't think so. You can actually squeeze gas, especially if you're into scuba diving. You can squeeze a bunch of air, put it in a tank, and breathe it later. So I'd say that it doesn't have a definite volume. Liquid, on the other hand, is really, 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 really hard to squeeze. It's not as easy as gas. So I'd say that liquid would be the best option here. Liquid, it's a lot harder to squeeze, has a more defined volume, but it doesn't have a set shape. And I know there will be people watching this video saying, well, that isn't 100% true. You can actually squeeze water a tiny, tiny bit. I'd say, well, we're not going to talk about extreme examples. We're just going to go with kind of real world cases here. It's really hard to squeeze water. All right. 23, a sample of ice at negative 10 degrees Celsius occupies 25.00 milliliters. What is the sample volume after the ice is melted and warmed to 4 degrees Celsius? And then it gives the density of ice and the density of water. All right. So let's think about how we would set this one up. This one's set up a little bit weird. So let's think about the sample of ice here. This is what we're starting with. And it says that it's 25.00 milliliters, right? Well, let's figure out what the mass would be, right? Because the mass isn't going to change during the process of melting. So what I would do is I'd try to cancel out milliliters of ice, and I would try to get to grams of water. How many grams of water are in 1 milliliter of ice? Well, let's take a look at what's provided down below. It says the density of ice at negative 10 degrees is listed here. So we can plug it in and we can say, well, it must be 0.9187 grams of water per every 1 milliliter of ice. So this is great because now we figured out the mass of our ice sample. And I can cancel out my milliliters and milliliters. All right, but it's not asking what the mass is of the water after it's melting. It's asking what the volume is. So here's where things get kind of into a story problem time. It's saying, what's the sample of volume after the ice is melted? So now what I want to do is I get rid of the grams of water by putting that on bottom. That way I can cancel out my grams unit. And then what I would do is I'd say milliliter of water in the liquid state on top. And that's where our second density comes in. So the density of water at 4 degrees Celsius is just 1.000 grams per milliliter. So I would just write 1.000 grams per 1 milliliter. So now when we see what's going on, we can see that our unit left over is going to be milliliters of water, which is exactly what we're trying to solve for here. So let's go ahead and check this on the calculator. And my final answer, I should have 4 sig figs in it. So I'm just going to keep things simple like that. My answer with 4 sig figs would be 22.97 milliliters of H2O liquid. Does that make sense? Okay. I know oftentimes with these, students know how to do the math, but they get really hung up on the word problem aspect of this. And for me, when I took chemistry, I had to just write down as much as I could on a page and just kind of mind map it together. And oftentimes I would run into dead ends or not know where to begin. But it's kind of like fitting a puzzle together. You got to find the units that cancel. So for example, trying to cancel out milliliters of ice would be my first step. And then I try to figure out where to go from there. But it's okay. The biggest thing is fighting that frustration, because sometimes you get that voice in your head where you're like, I don't know where to start, and you throw in the towel and you give up and you don't give yourself any time to even problem solve with it. So try to keep that little voice in your head at bay. And then even if you run into a problem where you're like, I just don't know, I struggled with it, don't let it drag you down for the rest of the exam. Everybody's allowed to make mistakes in life. And if you miss one problem, that's one problem. It doesn't mean that you're not a good student. So just brushing off problems that you struggle with is another key component to doing well. All right, only a few more problems here. So 24, write the complete electronic configuration of ground state sulfur. So here's what I'm going to do. I'm going to paste a periodic table down here. That way we can look at it with sulfur. Okay, and what I'm going to do is I'm going to do my trick that I prefer, and I'm just going to walk through the periodic table to find the state. So here's what I always do. I first start out by labeling my s orbitals, and it's pretty easy. You just go 1s, 2s, 3s, 4s, 5s, 6s, and 7s, right? And this is the S block right here. Make sense? And then next, oh, sorry, before we go forward, helium really should be right here, right? So it's also in the S block. Okay, next though, I would go over to this chunk of the periodic table. This is our P block. And the P block doesn't start at shell 1. It actually goes up a step to shell 2. So I'd say this would be 2P, 3P, 4P, sorry, this is cramped, 5P, 6P, and so on. And then next, I could go ahead and look at the D block. Luckily, sulfur isn't going to pass through that, but let's just do this for practice. For this one, we don't start at 1, we don't start at 2, we jump up a number to 3. So this would be 3D, 4D, 5D, 6D, and so on. And then last but not least, we've got the F block. What number do you think we start at for the F block? 4. exactly. I'm seeing people mouth it to me. I like it. So we've got 4F and 5F. So now we need to identify where sulfur is on the periodic table. But that's not too bad. Sulfur is right here. Right? So let's work our way almost like we're reading a book all the way to sulfur. Okay? So first things first, I'm going to go through the S block here, specifically the 1S block. So I'd write 1S. We went 2 spaces over, so I'm going to put that as a 2 on top. All right, so not too bad. Then we jump down to the 2S block. So 2S, and then we had to go 2 spaces over, so we put 2 there. And then next, we're going to go all the way through this 2P block. Sorry, this P block should go all the way over there. And in this case, we're going to pass all the way through it. So I'd say we went 6 places over, so I'm going to raise that to the 6th. And now we jump down to the 3S block. Just like we're reading a book, we'll go down to the next row. And we had to go through 2 spaces. Now we go to the next spot. And here's where we arrive at our position. So we're going through the 3p orbital to get there. But when I'm counting, I'm going 1, 2, 3, 4 spots over to get to that sulfur. So what I would do is I would write a 4 right here to indicate that we went 4 positions over to get to that sulfur. And this would be my electronic configuration for sulfur. Does that make sense?
Are we allowed to abbreviate it?
Oh yeah, are you talking about the noble gas configuration?
Yeah.
Yeah, absolutely. So let's do the noble gas configuration really quick. So the closest noble gas before you get to sulfur is neon, right? So neon is right here. So what we could do is just start out at neon and say neon is going to be my starting point. So I put it in brackets. But then the next thing that I go through is going to be the 3s orbital. And we could put the 2. And then same thing with the 3p. We went 4 spaces over. So I would accept either of these as being a valid answer for that problem. Sound good? Okay. I know the book doesn't teach it the same way like this. If you have another way that works better for you, you can stick with that. But this is personally how I learned it. It seemed to be more intuitive for me. All right, and this is a couple problems I actually copied over from another worksheet, just because I wanted to get some chapter 4 material on this review, because everything up to this point has been chapter 1 through 3. But which of the following compounds is most likely to have no net dipole movement? Let's first break down what we mean by dipole moment. What does that mean? Well, let's define this. It's an imbalance. Of electron density in a molecule. But in this case, they're saying no net dipole moment, meaning there's no imbalance of electron density in a molecule. So now we need to kind of figure out what's going on here. So let's go ahead and just work through these. So NH3 was actually one that you did in your molecular modeling lab. So if you have that work, you might have noticed that your model kind of looked like a little stool like this. That was the overall 3D shape. And then the next one was also in your modeling lab. And it looked a little bit different. It looked more like this. This is carbon tetrachloride. And then the next one, I'm just going to put underneath here, was water, which again was also in your molecular modeling lab. And it looked like this. And then the last one is pretty similar to B. it's still going to have a carbon with 2 chlorines coming off of it. But rather than 2 additional chlorines, the other 2 spots are actually going to be filled in by hydrogens. So you could work through and try to draw the Lewis structure for this. All right. So now we need to kind of work our way through this and determine if there's a net dipole moment in any of these molecules and which ones may not have a net dipole moment. So I'm just going to erase this to keep things from getting super cluttered. And I'm just going to write 18 here. And if we look at the periodic table, the periodic table has a nitrogen on it that's pretty close to the fluorine, right? So nitrogen is going to be pretty electronegative, and it's going to hog electrons from each of these hydrogens. Does it look like equal sharing, or does it look like one side of the molecule is favored? I'd say that it's not super equal. They're not going to cancel out. The net effect is going to be a pull upwards. So I would say that this has a net dipole. Okay, the next one. Chlorine is more electronegative than carbon, so it's going to tug electron density this way. But in this case, do we think that things are bouncing out or unbalanced? I would say based on 3-dimensional space, they must be canceling out, right? It's a tug of war kind of pulling in equal and opposite directions. So this would be no net dipole. Let's double check the other ones though. Oxygen in this case is more electronegative than hydrogen. So it's going to pull electron density towards it. And the average of these two is kind of going to be pointed up towards the oxygen. So I would say that this has a net dipole. And then let's check the other one. We already said that chlorine is more electronegative than carbon. And in this case, carbon is slightly more electronegative than hydrogen. So it's going to hog electron density. Does it look like everything's canceling now? Not really. It's not like over here, because we don't have chlorines pulling equal and opposite in all directions. In fact, the net dipole for this one is going to be more towards that chlorine side because the chlorine's pulling pretty heavily against that carbon. So this would have a net dipole. Okay, so it looks to me like the correct answer for this one would be B. But before we go forward, let's just double check our naming. Okay, so let's do our molecular geometry for all of these. What would the shape be for this one? Does anybody remember? For the molecular geometry, meaning the shape of just the atoms. I think you might be muted. I saw somebody trying to speak.
Isn't it tetrahedral?
So the tetrahedral would be the electronic geometry.
Oh,
But keep in mind that this lone pair isn't being occupied by an atom. What does that shape become if we swap out one of those atoms for a lone pair?
Is it trigonal pyramidal?
Yeah, exactly. Trigonal pyramidal.
Should we memorize all? Are we gonna get? We're not gonna have like a. Should we memorize all the names, or they'll just kind of? It'll be A, B, C.
So what I would like students to do is be able to differentiate what molecule is, linear, tetrahedral, trigonal planar, and trigonal pyramidal. Those 4 are kind of the extent of it. I'm not going to go into octahedral and things like that.
Okay, perfect.
Yep. All right. So that was good. Just simple review. All right. Kind of unrelated to the question, though. We'll finish up with question 19 here. So question 19, which of the following molecules has its central atom with an incomplete octet? So let's take a look at 19. And NF3 is going to look a lot like the molecule I actually wrote right above. NH3, but we're going to swap off those hydrogens for some fluorine atoms. And those fluorine atoms would each have lone pairs around them. All right, next molecule is H2O, which we already drew right above, which would look like that. Next one is BF3. We haven't done one for BF3, so let's try to build it. So BF3 has boron. How many valence electrons for boron? I checked my periodic table. It's in group 3A, which means it must have 3 electrons. So I'd go ahead, 1, 2, 3. And then fluorine has 7. So I'll go ahead and draw 7 dots around each of the fluorines. And then we need to pair up any unpaired atoms, or sorry, any unpaired electrons. So I'd pair these, go ahead and pair these, and I'd pair those, right? So when I go ahead and try to make this, we've got 3 fluorines around it. And the way I have it drawn right now, boron doesn't have a full octet, which is kind of interesting. And somebody mentioned earlier on that in one of my videos, I said that boron and a few other atoms are kind of the oddballs that don't always follow the octet rule. So in this case, the big clue would be that boron, anything in group 3A, doesn't always follow the octet rule. So I'd kind of probably stop at that point and just say that seems to be good enough. But let's do the last one. So germanium, if we look at it, is in group 4A. And so it must have 4 valence electrons. Oops. Let me zoom in more. I can't write a G. Come on. So I put 4 dots around it, and then it's got hydrogens with 1 valence. So I put those kind of staggered around it. And then same idea, I'd pair up those unpaired electrons, but we can see pretty quickly that germanium would have a full octet of electrons around it pretty easily by connecting all of these together. Let me make this G better. And there we go. So I'd say the boron trifluoride would definitely be the oddball here. Does that make sense? These two weren't on the original practice exam. I just pulled them in, like I said, to get a little bit more practice from chapter 4, because this practice exam I noticed was mostly chapter 1 through 3 material. Any other questions that people want to go over in the last few minutes here? Nope. People chemistry'd out for the day?
I have a quick question.
Yeah.
I tried exam 1 sample 2.
Yeah.
And there's one that has, it's a percent by weight question. It says, what is the percent by weight of sulfur in iron sulfate? And then it has a 3 in parentheses, like an exponent, and I don't know how to solve it.
Here, let me take a look at that really quick.
It's problem number 12.
Okay, just a second. I'll try to copy and paste it over, and hopefully that'll work. Okay, so let's go back here. And everybody can still see my screen?
Yep.
Okay, let's blow this way up. Okay, so this was the problem you were talking about?
Yeah.
Yeah, so this is a good question. So it's got some brackets around it. I would ignore the brackets, meaning right here and here, because they're on the outside, right? And
Okay.
there's no number out here to indicate that there's more than one of them. But let's break this apart. So we've got Fe2 and then SO4 3. Let's determine the number of atoms that we have of each type. So iron, for example, I know that I've got 2 atoms. Let's go to sulfur though next. How many sulfur atoms would we have in here?
1.
Not quite, because really what this is indicating is that this whole unit right here is
Yes.
multiplied by 3.
Oh.
It's saying we've got 3 of them in there. So with that in mind, I would say that there'd be 3 sulfurs.
Yes.
Yep.
That's, I can't get it.
Yeah, exactly. And then oxygens, how many would we have?
3? No, 4. Excuse me.
Not quite.
No,
Because just like we said over here, we've got 3 of those.
7.
So I would say we've got 4 plus 4 plus 4. So I'd say we'd have 12 total oxygens, right?
Oh.
So anytime you see parentheses with a subscript after them, it basically means whatever was in the parentheses, there's that many number of them.
Okay. Thank you.
Yeah, no problem. And then other than that, we would follow it kind of like we did in the practice exam. So we'd want to add up the mass for each one and then divide the part by the whole. Sound good? Any other questions?
Can I ask something about the lab real quick?
Yeah, definitely.
So for central atoms for CH2O, there's a carbon and there's also an oxygen.
Mhm.
I'm confused on how I would do the electronic geometry for that one.
Yeah, so this one is a little tricky. My hint is that carbon is always, or I should say carbon always wants to be in the middle of things. It wants to be the central atom. So let's try to even build this together. I'm fine doing this as a review session. If anybody's made it this far into the review video, they deserve it. So we've got carbon. How many valence electrons?
It has 4.
4. All right. Oxygen, how many valence electrons?
6.
Okay. And then we've got hydrogens. I'll just put them right here and right here. They should have 1, right?
Mm-hmm.
So the first thing I always do is pair unpaired electrons. So let's start with the hydrogens. Pretty easy. We could pair those, right?
Yeah.
And then we could pair these as well. And then oxygen and carbon could be paired right there. But are we done?
No.
No, because if we think about it, we still have unpaired electrons here and here. So what should we do to fix this?
A double bond with oxygen.
Exactly. So we could double bond this. So let's clean this up, make it look nicer. That would give us a molecule with 2 double bonds, or sorry, a double bond to oxygen and 2 lone pairs left over. And then we'd have 2 hydrogens. Does that make sense? Does that make sense?
I can't hear anything.
Oh no, can anybody else hear me?
Oh. Now I can hear you.
I can hear you.
Sorry, nothing like tech issues. Does this make sense now?
Yeah.
Okay, perfect. And then the next thing I would do is say, well, let's look at the central atom here, right? So this carbon, for example, would be the central atom. How many other atoms are bonded to that carbon? Well, I'd say it's bonded to 1 oxygen and 2 hydrogens. It doesn't matter that the oxygen's bonded to the carbon through a double bond. It's still just 1 oxygen, right? So it's got 3 bonded atoms. plus 0 lone pairs. We don't count the lone pairs on the oxygen because they're not on the central atom, which is carbon. So from this, we should be able to determine the molecular geometry and the electronic geometry. What do you think it might be?
Trigonal planar.
Yep, trigonal planar, exactly. And because there's no lone pairs, the electronic geometry and the molecular geometry are going to be exactly the same.
Okay.
Yep. The other hint I will give you if you're struggling with the molecular modeling lab is there's a link in the video, or sorry, in the handout to a PhET simulation, PhET. And if you click on that, there's actually an interactive building tool. And I don't know if very many students tried that out, but it will actually tell you the geometry and shape. So you can play around with it and build molecules and it will tell you the geometry and shape.
Okay.
Yep.
Thank you.
Yeah, no problem. Anything else before we close it up? All right, so just keep in mind, I'll push the exam due date back to Friday by midnight, but you're welcome to finish it earlier if you just want to get it off your plate. And then I'll send out an email tonight with the video and a reminder to everybody. All right.
Thank you so much.
Yeah, no problem. Have a good night, everybody.
Thanks. Have a good night.